Welcome to the channel. In the last lecture, I explained the semiconductor in its purest form, single crystal structure of silicon. In the silicon, forbidden energy gap is 1.12 electron volt, and in germanium, that is 0.72 electron volt. So acquiring 0.72 electron volt energy is very earlier than acquiring 1.12 electron volt energy. So electron volt pair generation will be maximum in germanium than in silicon, and therefore the conductivity of the silicon is less than germanium because of this forbidden energy gap, which is 1.12 electron volt maximum than germanium. So here at absolute zero temperature, silicon acts as an insulator, and at room temperature it acts as a conductor. So this type of semiconductor is called as intrinsic semiconductor, which is in its purest form. But remember, its purity is obtained by separate manufacturing process, where they are considering one part impurity only into the 100 million parts of semiconductor. Then this material is considered as intrinsic semiconductor. And here the electron hole pair generation and the motion of electrons and holes is random at room temperature. So random movement of electrons and holes at room temperature. Now we are going to move to improve the conductivity of the semiconductor material by doping process. So adding the impurity to the semiconductor material, this process is called as doping, and doped semiconductor is called as extrinsic semiconductor. So there are again two types, N-type semiconductor and P-type semiconductor. I mean to say N-type extrinsic semiconductor and P-type extrinsic semiconductor. Coming to the N-type semiconductor, in this case we are going to add the pentavalent impurity, for example phosphorus. So in the valence band there are 5 electrons, so we are taking one atom of phosphorus, here it is, and the neighboring silicon atoms. So in the valence band of silicon 4 electrons are there, and in the phosphorus 5 electrons are there in the valence band. 4 electrons in the valence band of phosphorus will form a covalent bond with the neighboring 4 atoms of the silicon, and there will be one extra electron which will come in the conduction band. So there will be extra one electron in the single structure of this semiconductor, which comes in the conduction band and which is free and will take part in conduction. So here this type of impurity giving one electron to the conduction band, so this type of impurity is called as donor type impurity, and in this case the electrons are majority carriers. Since this is tightly bound covalent bond, and the generation of whole electron pair at room temperature will be in small amount because of this impurity atom, and therefore the electrons are majority carriers. Now the next type is P-type extrinsic semiconductor, where we can add trivalent impurity, for example boron, aluminum. In the silicon atoms 4 valence electrons or 4 electrons in the valence band. In the boron, for example, there are 3 electrons in the valence band, valence shell, and therefore 3 electrons will be shared with the neighboring 3 atoms of the silicon and will form a covalent bond. And one atom will be trying to form a covalent bond with boron, and to form this covalent bond, neighboring electron will be jumping to form the covalent bond, and this electron is negatively charged, which is immobile ion, which is tightly bound in this covalent bond. So while moving one electron from this position to this position, what will happen? So in the next picture, electron will move from this position to this position and will form a covalent bond. Likewise, there will be 4 covalent bonds, but at the same time, hole will be generated when electron move from this position to this position. So in the original covalent bond, hole is generated, and second, this covalent bond is tightly bound, and therefore this type of material, the holes are majority carriers than electrons. And here boron accepting one electron from neighboring atom to form a covalent bond, this type of impurity is called as acceptor type impurity. Holes are majority carriers and electrons are minority carriers. Now, see the next situation. If you are going to increase the temperature of this, for example, N-type material, what will happen? At particular temperature, the number of electrons and number of holes will be generating in the same amount. Means with increase of temperature, because of thermal agitation, at particular point, at particular temperature, the generation of electrons will be equivalent to the generation of holes, and this type of material will be behaving like an intrinsic semiconductor. So if you are going to increase the temperature of extrinsic semiconductor, extrinsic N-type semiconductor at particular temperature, this temperature is called as critical temperature. The extrinsic semiconductor behaves like an intrinsic semiconductor. Thank you.